Welcome to ES 310 Lesson 9. Today we will move into looking at the second of three methods for solving kinetic problems that we will be learning about in this class. We will look at how to find the work on an object and then how to use the work energy method to solve these types of problems. For more information on this topic, you can see Hibbeler's Dynamics text, Chapter 14, Sections 1 through 3. As a quick overview of the class, these are the three methods that we will be learning about to solve kinetic problems. In the last few lessons, we've been focused on Newton's second law, which says the sum of the forces is equal to mass times acceleration. This is the ideal method to use when you're interested in things like involving forces and accelerations. You can, of course, use the kinematic equations to then take the acceleration and turn it into velocities or distances or times or positions. If, however, you're really interested in the force, velocity, and position, the work-energy method is recommended. As we'll see in the next few lessons, the work-energy method makes use of the fact that the kinetic energy, or the energy due to the motion of an object, plus any work done on that object, is equal to a final kinetic energy in another state. Once we've completed the work-energy method in the next four lessons, we will then learn about the impulse-momentum method, which is the third of our three kinetic problem-solving methods for this class. So let's take a little look at work first of all. This textbook and many other engineering textbooks use the letter U for work, probably to avoid confusion with W, which is often called weight. In some physics textbooks, you'll see other letters for these quantities, so just be aware that they have the same definition, they're used in the same way, but they may have a different name. So U 1 to 2 is the work done from position 1 to position 2. This is work done by a force when a particle undergoes a displacement in the direction of that force. So some component of the force and the displacement need to be parallel in order for work to be done. Which means if I stand in a classroom holding a textbook above my head for an entire day, I may be very tired, but I have not done any work. In fact, if I took that textbook and walked around the hallway around the science center for an entire day, I would also be very tired, but I also wouldn't be doing any work because the force on that textbook is gravity, which acts down. My motion, my direction, is horizontal. And so those two are perpendicular and no work can be done. So by definition, work is positive if the force and the displacement are in the same direction, and negative if they're in opposite directions. Mathematically, this requirement that they be parallel, or parts of them be parallel, should remind you of a dot product. So mathematically, the work from 1 to 2 is the integral from position 1 to position 2 of the force dotted with the position, or a dr. Graphically, you can find this by plotting F cosine theta versus S, and finding the area under the curve, which is the integral of F dotted with dr. The cosine theta is coming from that dot product. So if you remember back to statics where we looked at dot products, mathematically, if you have a vector dotted with another vector, you multiply the x parts together, and then you add the product of the y parts. Notice you start with vectors, but the dot product is not a vector. This is a scalar, right? No directions are involved. If you know the angle between F and ds, you get the cosine, which you can think of as if we break up the ds into components, right? One that's parallel and one that's perpendicular to F, then if this then is theta, then the part that's parallel to F is the adjacent to the angle, which is where the cosine's coming from. So don't memorize F cosine theta. If I gave you this angle up here, that definition wouldn't work. But remember that you need parallel components. If you have a constant force, you don't need to use this integral. You can just pull it out and use the component of the force. This is force parallel to displacement, right? So just as a reminder, those two components need to be parallel. So some special cases of work. We've got work done by or on a weight, right? So if we're talking about weight, weight is always going to act down towards the earth, right? Because the weight is the earth pulling on an object. And it's constant, right? So a constant force acting down is a weight. So it's going to be negative if we move things up. It's going to be positive if we move things down, right? Because a work is positive if we move in the direction of the force. So W is acting down, we move down, it's positive. W is acting down, we move up, it's negative. And the expression would be the force times the distance in the vertical direction, which are called y's. Okay? We can also get work done by or on a spring. Okay, so on a spring, the force due to a spring is Ks, right? So force due to a spring is Ks, where S is the deformation of the spring. This is not constant, right? Not constant. So we go to the integral expression. We're going from S1 to S2 of the force ds. We're saying ds is parallel to that force, right? The force on the spring is going to be parallel to the deformation of the spring. And so we have from S to S2, if we compress the spring, so if we go in this direction, if that's S, then the force is going to be opposite it, right? This is Ks. Likewise, if we stretch the spring and that is S, the force is going to pull it back the other way. So those two are always opposite each other, right? It doesn't matter which one you're looking at. So that's where the negative sign comes from. Ks is the force, ds is the displacement. If you do this integral, you get this 1/2 ks2 squared minus 1/2 ks1 squared. So you can just do the integral, or you can remember this expression. Notice there's a negative sign out here. So this could be rewritten as 1/2 of ks1 squared, which is the initial, minus 1/2 of ks2 squared, which is the final. So let's take a look at an example of this. We have a block. It is sitting on an inclined plane, and that plane is smooth. So there's no friction involved. We're stretching at a spring as it moves down. We're pulling on it, and obviously there's a normal force pushing on it. We're given a velocity, which we'll use later in this example. We're going to do the first part now, and then we're going to complete it later in the lesson. So we need to figure out the work done on this block. To figure out the work done, we need to know what direction is it moving in and what directions are the forces in, right? Because we need the parallel parts of the displacement and the force. So let's draw a free body diagram of this block. So there's our block. We've got mg, the weight, acting down. We've got F pulling it down the slope. We've got the force of the spring pulling it up the slope, and we've got a normal force preventing it from falling into the slope. Alright, so we have 4 forces acting on our object. Now we also need to know about the position of the object and how that's changing. So it looks like it's being pulled down the slope. S is defined as starting at the link where the spring is attached. I'm going to create a more handy variable called S prime, which is the distance that it moves starting from point 1. Alright, so the relationship between S and S prime is going to equal our total distance minus, so our total distance is S, right, as defined from up here, minus the initial length of S, which is 0.6, which also happens to be the unstretched length of the spring. So S prime is the variable, is the deformation of the spring, in addition to being the distance that this block is moving. All right, so we could possibly have work from each of these forces. All right, so let's talk about what all of those works would be. If we look at the Fs, or the spring force, the work due to the spring force is, if we look back at the previous slide, this expression, right? So 1/2 K1 squared minus 1/2 Ks2 squared. So 1/2 Ks1 squared minus 1/2 Ks2 squared. Well, in our case, S1 is going to be S prime equal to 0, right? Because it starts unstretched. So that's 0. And S2 is going to be just S prime. So 1/2 K S prime squared is the work from 1 to 2 due to the spring. And S prime is parallel to Fs. Okay, oh, we lost the negative sign. There's our negative sign right from here. Okay, how about F? F is in the same direction as S prime, right? We're both pulling, you were pulling down the slope and it's moving down the slope. So work from 1 to 2 due to F is equal to just F times S prime. And it's positive because they're in the same direction. All right, what about N? N is perpendicular to S prime. So that means the work from 1 to 2 is equal to 0. So the last one then, mg, the work due to mg is the work due to the weight. So what we want to know, the mg is not in the same direction as S prime. mg is the vertical direction it would move, right? So if we move, if this is S prime, we'll have a triangle here. This is going to be 30 degrees, right? Same as up here. So what we want is this side, right? That's the side parallel. So the vertical side is the side parallel to mg. And the length of that side is S prime times opposite sine of 30. And the force then is mg, and that's equal to work from 1 to 2 due to the weight. Alright, so our total work from 1 to 2 is going to equal negative 1/2 K. Let's plug in some numbers. K is, what, 200? Times S prime squared. We'll just leave S prime in our equation for now. Plus F times S prime, F is 100 times S prime, plus, there's no normal force, the weight part, which is mg, well, hold on, numbers again. M is 10 times 9.81 times sine of 30 times S prime. And that is our work expression at any arbitrary point. They wanted it S2, we could plug in S prime is equal to S2 minus 0.6 for all the S primes, and that would be our final expression. The other part of this that allows us to actually solve kinetic problems using this method is the incorporation of energy. So in this book, kinetic energy is called T. This is kinetic energy. I'm sure there is a historical reason for the letter T. I don't know what it is. Just be used to calling kinetic energy T in this class. In physics, you'll probably call it KE. You'll just have to be able to translate. It works exactly the same way. So the principle for work energy is that the initial kinetic energy plus the work is equal to the final kinetic energy. And that then allows us to solve equations. T, kinetic energy, is defined as 1/2 mass times the velocity squared. So let's take a really quick look at the derivation. More details are in the textbook if you really want to delve into it. But it's interesting to see this because the principle of work energy, where you talk about it as a second method, but it is derived directly from force equals mass times acceleration. It's another way of writing force equals mass times acceleration. So if we start from the force equals mass times acceleration equation, and we remember that we have this kinematic equation, right? That was the mixed one, ADS is equal to VdV. So let's plug this in then. All right, so force times ds is equal to mass times VdV. All right, that is coming from the fact that if we plug in A, right, we get this is equal to mass times VdV divided by ds, and then we take ds to the other side. That's where that expression comes from. Now we integrate this from S1 to S2. Those are our two positions. As we go from S1 to S2, we're also going to change our velocity from V1 to V2. So we're integrating both sides, and we get the integral of F ds, which is called the work, right, by our definition on the previous slide, is equal to 1/2 mv2 squared minus 1/2 mv1 squared. Well, t is 1/2 mv squared, so this is t2 minus t1. And that is where our principle of work energy comes from. So it's really just a rewriting of force times equals mass times acceleration. There's nothing really new about this method. It just is more handy in certain situations. So how are we going to use this method? You're going to draw a free body diagram, just like we did with force equals mass times acceleration. Show the direction of the motions and all of the force components parallel to it. So that's what we did when we were looking for work. Then we're going to apply the principle of work energy. Notice kinetic energy is always positive because the variable V could be positive or negative depending on the direction, but you're squaring it. So kinetic energy is always positive. Then U is positive if F and S are in the same direction. U is negative if they're in opposite directions. And we could write, just remembering back to the previous slides, U from 1 to 2, the integral version is S1 to S2 F ds. And if you have a constant, we remember what that is F S cosine theta, so you're finding the part of F that's parallel to the part of S. All right, so that's principle of work energy. Just a couple of comments on friction real quick, okay? So we know some things about friction from our own experience. Right? We know that we can get heat from friction. You rub your hands together, that's why your hands get warm, okay? If we treat friction like a force, it will do work, right? Because it's opposite the motion of the object. So it's always going to be doing a negative work, right? So this then is the work due to friction. Mu at n is the force of friction times S, which is parallel to that force, okay? So now let's take a special situation, do a little thought experiment, right? So this is the initial kinetic energy. This is the second kinetic energy. We can imagine a situation where the force we're applying is just overcoming the kinetic friction, right? So we're applying a force. All of that force is going to overcoming the kinetic friction. So none of it is going to changing the acceleration or creating an acceleration. So T1 is equal to T2. We can imagine that situation. That is possible to create, right? So that is telling us that the work done from the P is just overcoming, or the force we're applying, just overcoming the work done by the friction. The problem with that is that doesn't seem to account for heat. We know that friction is also going to be creating heat while it's sliding down this hill or being pulled along the floor, but there's no heat in this equation. And so then we have to talk about what's really happening here, okay? So in reality, friction deforms surfaces, so we can't really treat friction in pure dynamics, right? We need to be in strengths of materials or mechanics of materials where materials can deform. If you zoom way in on the surface, and that surface isn't really smooth, it's got friction because it's got all sorts of bumps in the surface, and the surface on the top also has bumps in it, and as you pull one over the other, those bumps are going to deform. All right, does that make sense? So those bumps are deforming, which means that the effective distance that this moves is smaller than the distance s that we physically would measure it moving, okay? The difference then between those goes to heat. So really, when we write this term, this work due to friction term, some of it is being counteracted by the PS, which is an external work or external energy, and some of it is internal, raising the temperature, and that just does not show up in our equations. We're going to treat this as if everything was external, but don't worry, heat is still allowed to be created because we're deforming things, and so one assumption counteracts the other assumption. So let's continue the example we were just working on. All right, so we had gotten to the point where we had an expression for work on this block. And the work from 1 to 2 was 100, which is this force, times S1 minus 1/2 of K. I'll just write it as KS dot S prime squared, where K is given as 200, plus the mg, the weight term, mg sine 30 S prime. Okay, so that should agree with our previous example. Yes, it does. All right, so that's our work. Now we need to apply work energy. We need to know the kinetic energy of the two. Okay, so we know initially that V1 is equal to 5, and we want to know when the block stops, so V2 is going to equal 0. So we have the expression T1 plus U from 1 to 2 is equal to T2. T1 is 1/2 mass times V1 squared plus U from 1 to 2 is equal to 1/2 mass times V2 squared. This is 0. So the kinetic energy, initial kinetic energy, needs to equal the work done as it slides down the slope. So we get, let's plug in some numbers, 1/2 the mass, which is, what's our mass, 10, times 5 squared, plus then the work expression, 100 S prime minus 1/2 of 200 S prime squared plus 10 times 9.81 sine of 30 S1 is equal to 0. So we have a quadratic equation of S prime. You can solve that. You get S prime. You're going to get two answers. One is negative 0.59 and the other is 2.088. The negative one doesn't make sense because that would be the block moving up the slope, and we're pretty sure the block is moving down the slope if the spring starts as unstretched. So this one doesn't make sense, so that leaves the positive one as our answer. We weren't asked for S prime, we want to know how far down, so we want to know S. So we get S is equal to S prime plus the original length, which is 0.6. So S is 2.688 meters down the slope. And then that then is our answer. All right, one more example. I want to throw in some NT coordinates because you haven't gotten away from them yet. So we have a cyclist. He pedals as fast as he can, reaches a speed of 4 meters per second at this point, and then coasts up the slope. And at some point he's going to stop, right, because he's coasting up this slope. He's going to stop, and we want to figure out how high is it that he gets before he stops. And at this point, what are the normal force and what is his acceleration at the point that he stops? Okay, so first thing we want to do is a free body diagram of the guy on this slope. Alright, so here's my very fancy bicycle drawing, a box. We have mg, the weight of the guy. We have n, right? And that's it. There's no other forces. We're ignoring friction, right? Neglecting friction. And he's no longer pedaling, so he's not creating a force pushing him up the slope. He's just coasting up the slope. So those are the only two forces. Because he's on a slope, we're going to use the NT coordinate system. So here's n, right, pointing towards the center of the curve. And t is the tangential part going in the direction of his motion. All right. So now let's talk about work real quick. What forces do work on this object? Well, if the force is perpendicular to the motion, it doesn't do any work. N is perpendicular to the motion by definition, right? Because the motion is along the curve. N is perpendicular to the curve. That's why it's normal. So N doesn't do any work. So there's the work due to N, which is equal to 0. Plus the work due to the weight. Well, so what's the work due to the weight? Work due to the weight is the weight times the height, which in this case the height would be y. That's what we want to know. How high does he go before he stops? Okay, so now we use our T1 is plus u from 1 to 2 is equal to T2. If he's stopping, T2 is going to be 0. T1 then is 1/2 m v1 squared, we know v1, right, is 4, plus mgy is equal to 0. So we plug everything in, and you can actually cancel the m's. We could do this part of the problem without even knowing how much he weighs. So 1/2 of 4 squared is equal to g times y. We can find y to be 0.8155. And we're in meters. Alright, so he goes 0.8155 meters high. So he's up here somewhere. Actually, he's probably here somewhere, right? If the whole thing is 4. He doesn't actually go very high. What's the x-coordinate of that point? Well, we know that the equation, right? So we can find the x-coordinate just by plugging things in. So x to the 1/2 plus 0.8155 to the 1/2 is equal to 2. So for x, we get 1.2033. Okay, so he's moved 1.2033 in the x direction, so this distance here. Nope. We're using the coordinate systems they've got, so this distance here is 1.2033. Alright, now we're done with the new stuff. We've used our work energy expression. We've found the height he goes to when he stops. That's as far as we can get with work energy. To find the normal force and the acceleration, we need to go back to force equals mass times acceleration. So, looking at our free body diagram here, we can write our force equations. in the normal direction, what do we got? We've got the normal force, that's positive, minus mg times cosine of theta, right? Because this would be, that's theta. So the n part is adjacent to the theta. This is going to equal mass times the normal acceleration, and the normal acceleration is v squared over rho. Mass v squared over rho. We know the speed at this point is 0, so this is going to equal 0, so we can find the normal force. Normal force is going to be mass times g times cosine of theta. What's theta? Well, theta is the slope of this curve at that point, right? So if we draw this curve, here it is, there's theta. How do we find theta? Well, we've done this several times. We have to go to the equation for the curve, and we have then that the tangent of theta is equal to DYDX. This is a y. So how do we find DYDX for this mess of an equation? Alright, well, let's do that. We're going to start, instead of trying to solve for y or x here, which gets all sorts of strange square roots, I'm just going to leave that equation in the form that it's got, we have it, and take the derivative of both sides. So we're going to take the derivative of this side with respect to x, and we're going to take the derivative of this side with respect to x. Derivative of 2 with respect to x is 0. Alright. The derivative of x to the 1/2 with respect to x is 1/2 of x to the negative 1/2. Alright, that's straightforward. The derivative of y with respect to y to the 1/2 with respect to x is the outer derivative, right, to the negative 1/2, times the inner derivative, which is dy dx, because y is dependent on x. That then is going to equal 0, so we can solve for dy dx. So dy dx is equal to, we move this over to the other side, there's a half on both of them, so we get, the halves are going to cancel, right? So we're going to get negative x to the negative 1/2 divided by y to the negative 1/2. And we have values for x and y. So here's the y, here's the x. Plug those in down here. We get a number which is negative 0.8232. Plug that in over here, and we can solve for theta, which I always drop the negative sign because I've reflected the negative sign in my triangle already. I know that this bottom line is a negative x. So theta turns out to be 39.46 when you take the inverse tangent. And we can go back over here to find n, right, is mg times cosine of 39.46, which gives us 568 newtons. So that's our first part, right? So that's the normal force. How do we find the acceleration? Well, the acceleration has two components, right? One is the n component of acceleration, which we've already said is 0, right? Because v is 0 at the point that it stops. And then so our acceleration is going to equal the tangential part of the acceleration. We can find the tangential part of the acceleration by looking at the tangential force equation. The tangential force is the only force that's acting tangentially as part of the gravity, right? Part of the weight. So we get that mg sine of theta is going to equal the mass times the tangential acceleration. Masses cancel, we solve for, so acceleration is equal to the tangential acceleration, which is equal to, if we plug things in, 6.23, and the units are meters per second squared.